through like the process.
Now everybody's afraid of not writing enough. Okay, here's where I started kind of, I don't know, I just felt like it was really vague. In your book, you give it a shot, read it. I don't think it's just me. It's so loosely defined. I don't know what they're talking about. I really don't. I read it and then I texted a famous game theorist and I asked him, what does this mean? And he said, I don't know. Maybe you should look up NIM on Google. And I said, I already looked up things on Google. So he took a picture out of a book, which is it's just as loose as what we have. And then he criticized the combinatorial game theory field for not being precise. So that means kind of there might not be anything out there that makes it precise. So it's annoying to me, and I want to make it precise. So they define the Looney state of strings and coins is one where no coin has valence 1. None of the coins in your palette have valence 1. And every coin of valence 2 is either part of a chain of at least 3 coins with valence 2 or a loop of at least 4 such coins. And what that means, I think, is that this is a chain of strings and coins. Each one of them have valence 2, and there's three of them. So there must be at least 3 coins with valence 2 in a chain. And what would a loop look like? That's a loop. So in this loop, every one of the coins have valence 2, and it comes around, and there's at least 4 such coins in a loop. So I think they're trying to do an if-then. So I'm going to double check this. So they don't have examples. This is just what I think they mean. I'd like to know for certain they mean this because they don't have that. If you're in such a stage, the player whose turn it is said to be in control. And what that means is if you're in control, you know what next moves you have to make in order to be the winner. I think. They never say so, but I think that's what they mean. A Looney position, they actually wrote this. In fact, they have a box here that's called any. So I think they mean anything. So a Looney position is one of the type where you have a coin, a string, a coin, a string, and anything can follow, except this picture can't happen, where you have coin, string, and that's it. So I think this is what they mean by Looney position. You can look in your book. That's exactly what it says. In fact, it doesn't say it like that. I'll show you what it says. Because I looked at this. It's not a sentence. Now you'll know why I ask you to always have clear sentences. You guys can help me interpret this. I looked at that for some time. Coin, coin, any is Looney, except coin, coin, coin is not Looney. That's a Looney sentence. It's not a sentence, right? And I thought, I looked at that for several minutes, and I thought, they must mean this is Looney as long as that any is not this. That's the only thing that I can think of that makes sense.
So as long as the last coin...
As long as it's not coin, coin, coin.
The last thing
I think they mean anything can be in there. And you'll see, I went through their proofs. I think anything can be here. Like I'll show you some examples of what I think they mean. So I reserve the right to change my mind after going through some other literature and trying to lock it down. But I think that's what they mean.
Well,
so I know you didn't believe me, but this is what they have.
I feel like if a coin's not there, then nothing would be there.
You'll see what I mean. I'll show you some pictures. Again, this is what I think they mean. So it's my interpretation of this. Okay. So they gave a chart like this, and they said some of the positions were Looney moves. And for example, they said this is a Looney move. So my interpretation, if I understood them correctly, is that they meant to take the string off on top that was there, and now you have coin, string, coin, coin, string, and then a coin with lots of other stuff around it. So it's not just dead end with a coin. I think that's what they mean.
Isn't that 3 coins?
So if you remove this one up at the top, you have coin, string, right? And then another coin, but it doesn't dead end in the coin because they said except can't dead end in the coin. That's my interpretation. I reserve the right to change that. So it has other stuff there. Here was another loony move. If you remove this one on top, right here, then you'll have coin, string, coin, and then string. So it doesn't dead end in a coin. I think that's what they mean. They don't want you to dead end into a coin. There's another loony move. I removed this piece right here. Now I have coin, string, coin, and then a string. It doesn't dead end in the coin. I'm not comfortable with it because I'm interpreting, and that's not what we do in math. We have precise language, so there's no interpretation necessary. So that's why I had talked to Dr. Jones to ask him, what is this, does this mean? And there was other, it's like you're taking circle to natural evidence to try to figure out what it is. They said this is a loony move. They deleted the string right here. It's a loony move because now you have coin, string, and then this extra stuff. Notice that the loony move in the dots and boxes is equivalent to starting to create a long chain. So now it becomes clear what the connection between the two is. They also have other language. They call this a double dealing move. So if you have somebody creating something like this, the obvious thing is you don't want them to have a long chain, so you want to block them from having a long chain. So they call this a double dealing move, which in the strings would mean that you're actually removing this and you're stopping that loony move. You're blocking the loony move, basically. And they call this the double cross move. If you decided to make a move like this, well, what's your next person going to do? What's the computer going to do? They're going to create boxes out of the remaining pieces. And so that's what they call a double cross move. Now, this is how they define double dealing move and double cross move. This is exactly how they define it. And then they go on and use it everywhere. So again, it's not good when I'm irritated. I was highly irritated because I wanted to know, what does this mean? I want a definition that works for all cases with symbols in it so I can get my hands on it. But we'll get that. This was my interpretation of what they mean. Sorry. So why are they doing all this language? It's why we do mathematics, why we put the machinery in mathematics. We want to prove something. So the theorem that they're trying to prove is that under optimal play, what that means is that both players are going to do what's best for them. From a loony position, the player to move next, the one that starts from the loony position, can get at least half of the remaining coins. I think there's more assumptions to this theorem that they haven't stated too, and I'll show you why. Because if I go to the proof, how do you prove that? Suppose player, call it Alice, is up. It's their turn. And suppose she can move on a loony position. So she has, this is the loony position she's starting out with. My guess is that they meant that she has only the loony position left. That's the only one she has left. That's what I think they meant. I'll tell you why as I go on through the proof. So this is what she can do. That's where she can start with. If you make the assumption that this hidden box, where there could be all kinds of weird stuff in here, if you make the assumption that if you play in this box you can pocket n coins, then what Alice can do, she has a couple of choices. Her first choice is that she actually plays so that she removes this, and she actually takes all those n coins, and then it's still her turn, so she removes that string and that string for a total of n plus 2 coins. So that's one possibility. She went to the hidden box, got all those n coins, and then she removed the 2 strings, so she has n plus 2 coins. The other possibility is she could sacrifice the 2 coins here, so she doesn't get them, and the opponent is the one that gets up to n plus 2. Well, in that case, Alice can get all the n plus 2, or she gets everything but the n plus 2 coins. And the total number of coins is obviously n plus 2 or plus the total number of coins minus n plus 2. I should have put parentheses around there. So one of those two numbers is at least half of the total. Has to be because of the plus 2. And that's why. So based on this proof that they have in the book, the assumption must be that she has only that loony move to position off of. Because if there's other weird moves left, then it wouldn't make sense. Then the second player could go do things. Okay, we're going to stop there. What we're going to do next week is I do want to formalize this because this feels kind of hanging to me and I want to see what the structure is, so I'm going to get that for you. But I want to give you a couple of other games because we're getting closer and closer to the deadline for choosing your game and what you want to do. So I'd like to also introduce some more games so that you see them. There are some in your book, and that'll give you more an idea.